systems are, as the name implies, connected directly to a utility grid. In this lesson, we will discuss what a grid direct system is, as well as where grid direct systems are commonly installed. We will see what equipment is required in these systems, and we'll talk about how energy flows through a grid direct system. As I mentioned, grid direct systems are connected directly to a larger utility grid. These systems do not incorporate batteries or other types of storage, and they don't have any charge controllers, and therefore they tend to cost less and require less maintenance than a standalone system of comparable size. Grid direct systems require a functioning utility grid to operate. That means if the grid goes down, the PV system also goes down. A grid direct system can't function as a backup power source in the event of a grid outage. This is a key point to be aware of when you are dealing with grid direct systems. There are two generation sources present when we are talking about grid direct systems. One's going to be the PV array and one is going to be the utility grid. We also have conversion in the inverter and our consumption at the AC service panel, which is also typically going to be the point of interconnection, or the POI, to the utility grid. DC energy flows from the PV array to the inverter, where it's changed to AC energy, which powers the AC loads of a building through an AC loads panel or a main service panel. Any excess electricity is sent onto the grid through a point of interconnection with the grid, which is commonly going to be at the main service panel. At night, when the PV array is not producing power, all the loads in the building are served by the grid. The inverters used in grid direct systems are specifically designed to shut down when the grid goes off. This is a safety feature, which is intended to prevent injury to any workers who may be fixing the grid nearby. If the PV system did not shut down, it could continue to send power to the grid during an outage and potentially injure any line workers nearby. Again, when the grid is down, there is no power to the system at all. PV power will not be available if and when the grid goes down, even when the sun is shining. So they can't function as a backup system. Grid direct systems are common in many different applications, and on this slide we can see a few residential examples. The PV array is usually installed on the roof, possibly on the ground if there's enough space, and is connected to an inverter which converts the DC power to the AC power, which is used by the house loads, and any excess power is sent to the grid. The photo image in the middle here shows sort of a blown up side wall picture of this house. You can see there that there's a meter and an inverter and some other pieces of equipment that are associated with smaller grid direct residential systems. Commercial grid direct systems are also very common and are essentially just larger versions of residential grid direct systems. They tend to have more components, more complexity, larger size, but the concept is the same. There will be two sources, the PV array and the grid. In this case, we can see the array on the roof of this building, and then coming off of the roof in large conduits to 3 inverters. On the left, you can see we have our inverters going into an AC combining panel, which is right in the middle, and then that goes into a meter and then to a system disconnect. The largest types of PV arrays that are grid direct are utility scale PV power plants. These systems are typically going to be ground mounted systems that are connected directly to the larger utility grid and don't serve the loads of any buildings directly on site. The energy that's generated by a PV power plant becomes part of the larger mix of sources that contribute to the energy that the utility grid supplies. These systems typically have a very large PV array, many kilowatts, hundreds of kilowatts or multi-megawatts even, which can cover many acres. They may have one or more large central inverters, a meter, and often transformers, which will step the PV system voltage up to match the higher voltages of the utility grid lines where the system is connecting. With the PV power plant, we still have two sources of generation, the PV array and the utility grid, and we have our conversion taking place at the central inverter or inverters. This is an excellent example of a utility scale PV system. Many of these systems are owned directly by utilities and can provide power to the surrounding areas. Inverters are spread throughout the array. It's the little white boxes you can see kind of dispersed within that array field. And they are connected to the substation in the lower part of the image where the utility point of interconnection is located. Grid direct systems differ from standalone systems in that they are connected directly to a larger utility grid and will not function when that grid is off. Grid direct systems function very well in residential scale, commercial scale, and utility scale applications. Conceptually, they are the same throughout all those different types of systems. They just tend to have larger and more complicated components as you get into the larger scale systems. These systems do not utilize any storage, so they tend to be a little bit less costly than systems that do of the same size.